Hello, my name is Kyle Markovica, and I'm going to show you and tell you how to design and build a Formula FSAE rear suspension bulkhead. First of all, our project statement was to redesign the University of Nebraska's Formula FSAE 2015 race car. To do this, this is the original race car from prior years, and as you can see, it's a square design with the control arms connected to a stainless steel tube chassis. This chassis is welded together, and nodes are welded to the frame where the control arms mount, bell crank, anti-roll bar, and components such as that. What we're trying to design is something sort of like this that is more precise and will get better performance out of the race car. In order to design this and build it, manufacture it, and have the complete package, we started with Optimum Kinematics. With Optimum Kinematics, it's basically a tool that designs suspension. It will get us geometry and everything that has to do with that. From there, we plugged it into SolidWorks, and as you can see here, here's one of our designs, one of our iterations, and from there we took the components and put them into Adam's car. With Adam's car, we are able to adjust all of the hard points for the bulkhead, such as the control arms, the bell crank, tow bar, anti-roll bar, and every component that is situated in the rear end of a race car. This race car goes through different tracks such as straight line acceleration, long sweeping curves, and everything is timed. And in order to get higher performance, we need to have more precise nodal positioning for these components. As you can see here, it's not very good. And with this, we machine it, and everything goes exactly where we want it, exactly where we want it placed, and it is perfect. So performance will increase drastically. And in order to manufacture this, as you can see, it has an aluminum bracket on top, aluminum bracket below, and a differential mount in the center. This piece is made out of aluminum bar stock. This stock is machined by a CNC mill that goes through each deal and goes through the center to make lightning holes. These lightning holes will decrease the weight of the bulkhead, in turn increasing the performance of the race car. And major desired outcome of this is to reduce weight, increase manufacturability, and reduce the wheelbase of the car. So if we reduce the wheelbase of the car, we are able to reduce the yaw moment of inertia. And basically, yaw moment of inertia is how when a car turns and it starts skidding out, we want to reduce that. We want to put all the power to the ground and be able to take it to the track and perform much better. So after we designed this, we put it all together, and after 4 or 5 iterations, we started out with a solid aluminum block, went to 2 sheet metal plates, and then we came up with this hybrid design with aluminum, and then on the sides you can see is a sheet metal. And that is where our control arms attach directly. After we designed this bulkhead, we did the finite element analysis. With finite element analysis, we take the forces that we found from Adam's car and place it into this software, which will tell us a factor of safety, tell us whether a part is safe or not to drive, and whether it will buckle, break, fracture, typical things like that. So with this design that we made, the factor of safety was actually 1.3, and they only asked for a factor of safety of 1. So actually our design is very well designed, very light. With this design, we have about 15 pounds of weight, all combined within that. With this, we have 9 pounds. So next I'm going to show you some of the simulations that we got from Adam's car and how we got the forces and everything else. So as you can see here, this is a straight line acceleration. The car is going down a straight line at 80% throttle. Here's another straight line demonstration, and as you can see, it starts going slow and then it speeds up. This will give us different types of forces, and that is what we put into our finite element analysis. To get our maximum forces, we actually put the car into the program and did a 100-foot radius. This 100-foot radius will give us the maximum forces that will ever be put into the bulkhead. And here is a drift-in animation. This is just another capability that Adam's car is able to do. Here's a final bulkhead that I drew up in SolidWorks.